Hello. OK, sorry. I was so nervous my computer wouldn't work. I asked the AV guys, is anybody else using Linux? And they were like, no. OK, here we go. So I'm here to tell you about TypeScript performance, what it is, how to measure it, then improve it, and keep it that way. Along the way, I'm going to tell you why you should care now that all you do is babysit AI agents. We'll look at some perf tools, and we're going to learn more about how the TypeScript type checker works under the hood. So if TypeScript is literally just a type checker on top of JavaScript, and JavaScript is the thing that actually executes your code, usually performance means runtime performance of a JavaScript engine that executes your code. For example, V8 is the JavaScript engine that powers Node.js, Dino, and Chrome. And JavaScript Core is the engine that powers Safari and Bun. So when I say TypeScript performance, I'm talking about how long it takes to check our types. And anything else is how the engine runs your code. If you care about runtime perf and you can't rewrite it in Rust, then try Dino or Bun if you're stuck with JavaScript. So at first glance, it might seem like the type checker perf is not as important as JavaScript perf. And yet, better type checker performance was a top community request for so many years that the TypeScript team recently ported the entire TypeScript compiler to Go because of it. And by the way, I'm going to pretend like we're all running TypeScript Go, because if you have a TypeScript performance problem, there's nothing you could do that would have a greater immediate impact than just updating to TS Go. It should be a smooth transition like every other TypeScript upgrade you've ever done, except now your code will type check 10 times faster. So why was this a top community request for so many years? Because there are three main areas where TypeScript performance really matters. The first is editor experience. We've probably all experienced the situation where you open the editor and everything just feels real slow. Like maybe you hover your mouse over a type and you get this little loading dialog, or maybe you can't go to definition or something like that. Another reason is that AI agents love to type check their code before handing it back to you, and that's because they're terrified of their own shadow, and passing type checking actually gives them a lot more confidence. So that means that type checking can quickly become a massive bottleneck for agents because they do it as part of their development loop. Third, type checking synchronously blocks your build early in your CI pipelines, and so everything else has to wait on it. I know there are a lot of ways to arrange CI, but a pretty common one is to put type checking early on. And every second seriously matters when you consider the uptime guarantees of serious companies. Your buddy's personal Minecraft server probably has 2 nines of uptime because it can be down for 3.5 days in the year. By the way, there's a trademark on the creeper face, and they'll actively sue you if you use it. So let's just roll the dice together, shall we? 3 is end-user services, 4 is cloud providers, and at 5 nines, we have more focused things like payment processors. And at 6, it really only gives you 31 seconds to be down cumulatively throughout the whole year, so it's only really like life or death things like high-frequency trading, also NASA missions. So Claude's uptime is even worse than your buddy's Minecraft server, only reaching 1 9 of reliability in the past month. But don't worry, GitHub has you covered with 4 8s, that is. So you better believe that extra 3 minutes wasted on type checkers is a pretty urgent problem for a lot of companies. And if you find performance problems in one of these domains, where do you look? What exactly is the type checker? So just think of the type checker as literally a function that takes some source files and options and returns error diagnostics if it finds anything wrong. And actually, by the way, it literally there's this checker TS file, and it's like you can't even open it on GitHub because it's so large. And that's really the architecture of TypeScript for real. So there are 3 main ways that the function is exposed at first. It's a command line interface tool for one. And so you can see this in your package JSON scripts and CI pipelines. The binary itself is called TSC, which is short for TypeScript compiler. And you get it by adding TypeScript to your dependencies. The CLI is what runs on your CI pipelines when you build. And number 2, we have the type checker language server protocol server. What is that? So in the olden days, every code editor had to individually add support for every language, and it was terrible. It was terrible for the languages, and it was terrible for the editors. Feature coverage was inconsistent, development was slow, and smaller languages were basically ignored. The LSP changed all of that by being the central abstraction languages could make servers for and editors could make clients for, so everyone just implements LSP, and boom, editors get more language support. Then new languages like Gleam can ship faster editor support without editors even having to know that Gleam exists. The LSP actually was modeled on TypeScript's own implementation for VS Code. And hilariously, the standards process ended up with something that diverged so incompatibly that TypeScript had to implement a wrapper to support it. And then 10 years later, when TS Go came along, they took the opportunity to write a normal LSP implementation from the ground up as part of the port. But I just think it's funny because now they're finally aligning with the specification that was based on them in the first place. So the LSP is what runs in your code editor. Now, last of all, the type checker is an API, sometimes also called an SDK. So here's an example of the TypeScript compiler API. Everything you need is from the same TypeScript package the CLI came from. if you make a JavaScript function and pass some names and tsconfig options, which, by the way, exact optional property types is one of the most important options people overlook, and it's critical to turn it on if you're your library. I know that sounds super nerdy, but like the library authors are listening. Then ts create program creates a source file and gets everything together. And then the type checker happens, the type checking part actually happens for this function get pre-emit diagnostics. And I think that's sort of funny that they called it something so cryptic, but that's nerds for you. They couldn't help themselves. And then everything else is just getting the info back to the user. So it's mostly tools that use it's mostly tooling that uses the API. So if you're running some kind of tool like a linter or a build tool and it's slow, it might actually be going through this path and not the CLI like you might think. So you really need to be aware of all these paths when you're seeing slowness because you measure all of them a little differently. So let's measure one. The easiest way is a CLI flag called extended diagnostics. And that shows the compiler performance stats. So some of it's static, like number of files, lines of code, counts of type instantiations, and symbols and types and stuff like that. And then there's some more runtime information, like memory stats and time spent on various part of the type checking phase. So let's type check a single file. It's got a person type with a name and an age. It's got a function that uses it. And then I can call that function. So if I run extended diagnostics on this file, I get these stats. If I add an optional email property to this person type, the count of type identifiers goes up from 47,665 to 47,666, and the type symbols goes up by 1, too. But did you notice that weirdly large number? It's like this was like a small file. Why are there thousands and thousands of types? And also, did you notice that it says 52 files and 55,000 lines of code? I thought there was just one file. So you dig in, and there's also this list files flag that will show you all the files that were included in the compilation. So here's the full list. It's got the ES5 types, the DOM and web worker types, the types for ES 2015, 16, 17, 18, 19, 20. We got the decorator debacle in there. And then finally, our single source file. So these files contain TypeScript utility types like partial, pick, and record, and definitions for things in the JavaScript standard library like array.find. But this concept is something that's actually really fundamental as a misunderstanding that I see people have when they're measuring the performance of their code base. It's really critical that you just accept that the moment you create a bundle or type check on a code base, that you are the proud new owner of every single character of code that goes into that compilation. Sometimes you generally included code that's outside of your package root by mistake. In that case, you should really check out TurboRepo's boundaries feature. It's incredible, and I just feel like a lot of people are sleeping on it because, yeah, well, it's in TurboRepo, but it's really useful for that particular job. So if you're digging in and you just ask yourself, you have to ask, are you a lib or are you an app? And that's because that's funny. Someone's head just went like that. OK, I think I figured it out. I gave a dry run of this talk like an hour ago, and someone laughed at this slide, and I didn't know why. It's not the word to be confused by, actually. I used to do Next.js development, and I would always get hungry, because to me, an app is the thing you order at a restaurant before the rest of your food comes out. And yeah, but anyway, you have to think about this spectrum, like libraries versus applications, because if you have performance problems in your application, you probably already know it just by using the application. But if you have a performance problem in your library, it's a lot harder because your code is probably only exported without being used elsewhere in your code base, or it's only really used in tests. So I'm about to show you an approach for performance problems using JavaScript, because all the same skills apply that you would use if you were type checking and doing type performance analysis. So here's a top 10 function. It takes a list of numbers, it sorts it, and then it returns the first 10 items. Typical tests for this look for like different kinds of numbers and checking how the function responds to invalid inputs and stuff like that. But we almost always write tests for correctness, for accuracy, but not performance. So let's look again at our function and try to find a performance problem. The most obvious thought might be, what if the input array is really big? If we try to measure that, how big can that array actually get? So if you look at the JavaScript spec, it says that arrays can get up to 2 to the 32 size items. And there's an exception made for the specific index, 2 to the 32 minus 1. So the max size is around 4 billion and change. Here's a one-liner for making an array of an arbitrary size, where I provide a 10, and it gives me 10 random numbers. But if you actually try anything over about 2 to the 27, it crashes. And it's that easy. You too can fail your next performance review by believing the JavaScript language spec. Ask me how I know. So we settle for 2 to the 26, and we get our pitifully sized 67 million item array. And when doing performance analysis, you have to be really careful when you're dealing with big numbers, because exponential scaling, 2 to the 32 and 2 to the 26 might seem like they're roughly similar in size, but they are absolutely not. So now let's think about our code with huge arrays in mind. Notice that it sorts the entire array, and then just throws away all that hard sorting work except for 10 of them. Ask yourself, if I gave you a list of 100 items and then I asked you for the 3 biggest items in that list, do you care if the 67th item is greater than the 68th? No, you just sort the 3 you're keeping, and you only need to check if each item is greater than your current smallest keeper. So by definition, 97% of them won't be, so we can just move on. And yes, making this change looks like a lot more code, but if you could read the native sort code, it would look like a lot of code too, and you should feel better to know that our optimization took us from 50 seconds down to 0.4 seconds. And here I need to stop and tell you something. It's about performance testing, but it's really career advice. The first thing is that no one really bothers to measure performance. I've been lucky to work at some amazing companies. I was previously at Verison, and now I'm at Cloudflare. And both are absolutely jam-packed with literally some of the best engineers in the world. Yet I've been able to put up PRs with tiny changes that have literally tens of thousands or hundreds of thousands of times improvements in type checker time. And it's not because I'm some genius. It's because people tend to only look into performance issues when something is going horribly wrong. And these big perf wins are just kind of like scattered around your code bases waiting for you. And when you do, you'll be shocked at the reaction. People get really excited about performance wins. I don't know how to explain it. It triggers this like caveman response where better number, make stock go up, and money go big, and money big good, stock up good, numbers low bad, bigger bar better. OK. Last, this is an area that AI is miles behind because AI code reviewers can't really measure performance. In April 2026, at least, they can review logic, but if you claim that a change improves performance with data points that appear legit, an AI code reviewer can't really argue with you because they don't run in environments where they can actually measure it. All right, so 113 times faster is great. Can we do any better? Let's think about the inputs. Numbers in JavaScript follow the IEEE 754 floating point spec. And by the way, that's the Institute of Electrical and Electronic Engineers. That's the real name. They really wanted to be welcoming to electrical engineers, but didn't want to scare away any of the electronic engineers. So this spec is why 0.1 plus 0.2 doesn't equal 0.3, which, by the way, is true for Rust and Go and C and many more. And there's a lesser-known optimization built into JavaScript engines that we can use called typed arrays. So for example, there's a float64 array that we can use. And just switching out our regular array for a typed array gets us 888 times faster. So notice the 2 optimizations we made were completely different approaches. First, we optimized the algorithm internals, and then we looked at external inputs and gave the runtime better information to work with for its own little internal optimizations. Can we do any better? So at this point, it's important to reevaluate and see if the thing that you were improving is actually still the bottleneck. You know, it might be, and sometimes it still is, and you can do a whole total paradigm shift. I measured this exact same thing with Rust, and it mopped the floor with JavaScript. But what's all this got to do with type checking? This is exactly the same process you go through for testing types. You might try to find a similar way to do the same thing. That's optimizing the algorithm. Or you might look at giving the compiler better information. So that's optimizing the inputs. And sometimes you do need to just like burn the house down and build it again. But this spectrum between libraries and apps exists too. But now there's this other spectrum to consider, which is how much your code base is full of types, right? So there are some code. If you put this together, by the way, you can make this quadrant, right? And it's not the kind that your companies lie and cheat to get onto so they can fundraise off of it, but it's similar to that. And we only have JavaScript libraries in the top left corner, right? These are things like Lodash from the olden days, right? And then in the bottom left is types-only libraries. I think the most common of which that we all use is Typefest. In the top right, it's harder to find some of these days, but they're like shy about it now. But there are still JavaScript-only apps out there somewhere. They're not listening to this talk anyway by now. And so altogether, most code these days falls into this highlighted area. But what's that area in the bottom right? So maybe you heard of this project getting doomed to run completely within the TypeScript type system. Thank you. Yeah. But I'm the author of that project. It's a big portion of what brought me to get more involved and interested in TypeScript type performance, of all things. So if you're interested to know more about that, Dylan Mulroy and I did a 6-hour stream going into all the technical details of how it all works. But I only bring it up because in order to get Doom working, I had to learn about exactly how much time the type checker takes to do its work. Even just figuring out what metrics correlated to time took a lot of effort because I had to make all of my own tools. So as silly as that project was, I took everything I learned about TypeScript performance and making Doom happen, and I packed it into a tool that you can use on your code bases called TypeSlayer. Doom, by the way, used the API, like tools do sometimes. But what about measuring the rest? How do we profile LSP performance, for example? So that's what TypeSlayer's purpose in life is. And measuring and identifying TypeScript type performance is its whole thing. Oh, well, I spill water over the stage. Don't worry, not on anything electrical, I hope. OK, all right. So let's do this. You ready? All right. So I'm going to pull up Excalidraw here. So I already did it, but You've used Excalidraw, perhaps. It's a nice, big, open-source app. And Excalidraw, I just go there, and I type npx TypeSlayer, and then it's going to pull up this app. Let's see here. So this is it. This is the first screen that you see. And what we're seeing is the package JSON of the thing that we're actually targeting. We have some flags that we can customize. Some of you really want more flags. So like, look, we can just like give it new. We can give it new memory. We can say, yeah, you might need a bigger stack in Node.js, whatever you need. And then I can click Run Diagnostics. What it's doing now is it's running TypeScript internal stuff, and it's grabbing information out of TypeScript for all the stuff that's happening in your application. So all of your types, everything in there. There's a generateTrace flag if you've used that before. Oh, there's a fun moment coming. Can we clap when we see it? You're going to see it. It's going to be amazing. Ready? Hey! OK, good. I'll remember this. That's how I feel every time I see this. So what is this? This is all the types in your library, all of them. And these little connections between them are the ways that they're related to each other. So if I click Filter Relations here, we can get rid of some. So like, let's just get rid of, we have none. So those are all the types, little tiny dots. We can just click Union. So like, what is a type here? I'll put all on, maybe. So what is a type that's in a lot of unions? Shout it out. Anyone think of one? Null. OK, yeah, null is one. OK. I think we might be able to get it. So I'm going to pause the little guy from moving here. Let's see if we can grab it. So I'm going to click a type here that I see has a lot of things. It's undefined. OK, yeah, close. So undefined is present in a lot of unions, right? Because you do like string or undefined. And so this is showing you all the relations between things. We can probably find more if we poke around. I've spent a lot of time poking around just for fun. Like here, let's do this one. It's probably going to, well, I think I know what it is. Let's see. Is it the Anthropic logo? No, it's array. So yellow is instantiated by, I believe. So we instantiate a lot of arrays. This is why there's these connections. OK, so this is all fun, but what's it for? It's for finding those problems. And sometimes because you might have an out of control, like you might have a union with 100,000 members, and that takes a lot of time for the type checker to calculate all of that. And so what's happening here is we're seeing type metrics based on the kind of relation. So this is a union with 981 union members. And here's the list of all of those members of that union compiled out. We can do the same thing from the other direction. So undefined is present in 6,244 unions. Same, and then null, whoever shouted out null. There you go, number 2. There you have it. So we can keep going and talk more about like kind of type level trivia. This is one that I'm excited about is actually these type level limits. If you're a library maintainer or you're in a monorepo in a large company, you might have this worry that, have you ever had a depth limit, recursion limit, or there's some like TypeScript error that it says this was a complex type, how do I compute it? And you're like, oh, TS expect error, maybe, and you just make it go away and nobody notices and you merge the PR. Well, you can use this tool to find all of those TS ignores that you put in there that you're trying to hide, so you can't hide anymore. Also, duplicate packages is a thing. So actually, Excalidraw is excellent. A lot of times when you pull up a new project, there's lots of duplicate packages in there that are part of the TypeScript bundle for some reason. I don't even know why Vite is here at all, because you wouldn't think that it would be part of the overall type check. It's a dev tool, right? So I don't think they're bundling Vite and Excalidraw, but maybe they are. And they're bundling 2 different versions of it. There's more we can do. There's like type trivia. This has this doesn't really need to be done, but I just thought it was fun. There's 93,000 objects in this particular project. Type relations. What I've done is tried to make all of this really accessible. So for example, this one, there's like a mini blog post that's written right there into the app that explains what all of these numbers are, how to think about them, what they mean with real examples. Some of them are a little more concrete than others. So this one here is kind of fun, largest display value. So this is a almost 1 megabyte sized JavaScript string literal that's 4 times duplicated in the code. Here's another one, reduce write. So reduce write is like this stuff here that we're seeing is all of the contents of this type. If you were to write this, it would be this big, right? It shows you there 119 kilobytes. You can click a little, actually, I'll show you that in a second. You can click a little search icon there and go to a search module, and you can see all those types and all of their relations, and you can search them by ID. I don't have time to get into how the ID system works, but TypeScript creates a unique ID like you might expect them to for every single type in your project, and you can sort of just see where all those types are. There's just random types here that I'm flipping through, but you can get more information, including, let's see if we can find one. including where that type is actually declared in your project. So you can click on it. So OK, this one is not in the Excalidraw code base. I'll find one in Excalidraw. You know what I'll show you next is type. We're almost out of time for this, but tree map shows you all the files in your project and how much time it took to type check those files. So you can see that app.tsx is the file that took the most time to type check in the Excalidraw code base. You can pull this up into the Perfetto module. Perfetto is a well-known tool for this. And I bundled it in here. So I can search this particular file name, and then I can go look for that particular file. It's included in a couple other files, too. And then here we have it. So you see that it's this big section here, create source files. So these are all different source files. And we can go to some of them and then try to see if we can find a particular type that we can trace back to the Excalidraw code base. Very often, so you see we have source ID here, right? So these numbers are the IDs that TypeScript assigns. And they can be very cryptic, and it can be very difficult to link them back. And all of these paths here are linked back to the code base. So I can click this particular path here, and it's going to open up Excalidraw at that point where that type was declared. So now you can go back to your code base and find it that way. All right, there's probably more. There's an MCP server, so you can have your MCP find the duplicate packages. There's a leaderboard so that you can see if any of the things that you're doing are normal or weird. Sometimes people ask that question. Well, let's get back to the slides here. So that's TypeSlayer. Hope you like it. Thank you. It doesn't. You just do npx TypeSlayer. I don't keep a change log, and since day one, the entire commit history was Eminem lyrics. So every release is a pleasant surprise. Is that funny? I can't help it. There's a funny thing on that. I used like a code to release it, and it's open source, so someone could go look at the code and see how it was generated to reverse engineer to get their own code. But I also used Eminem lyrics for the code, and then so when people were trying to reverse engineer it, they would pass the file, the open source file, to Claude and say, hey, give me a code for this, and he'd say, I'm sorry, I can't work with copyrighted materials. I didn't plan that, but now I try to pretend that I did. So what else is out there? Andrew Branch from the TypeScript team wrote he's like the world's top expert on module resolution. And he made this tool called Are the Types Wrong? And you just enter an npm name or tarball. So here I entered Next.js, and it shows me any module resolution or type bundling problems the project has. You get a detailed description of what's wrong, what will happen if you don't fix it, and also how to fix it. So you can run this on your CI to prevent yourself from accidentally breaking your package, which is really great. Obviously, it can't keep you from making horrifically bad design decisions like file-based routing that the type checker can never type check or assert on a file name. I'm not bitter. However, Andrew has a 50-minute video on YouTube about it, if you're interested. Another is by Orta Thoreau, a previous member of the TypeScript team. Here it is. It's called 2/. If you Linux, We good back there? Is it me or is it you? Well, they're walking out here. All right, I'll tell you about 2/ while we're figuring that out. So 2/, it's called, does anyone know why it's called 2/? It's kind of in the name. Because you started with 2 slashes. OK, badum-tsh. So 2/ is, you put a little caret. So 2 slashes, I'll act it out for you. So there's a slash here, there's a slash here, there's a caret, and there's a question mark. We coming back? Yeah? Oh, somehow. OK, so the way it works is I'm going to show, you'll see on the screen when the screen comes back. If you have an array of numbers and you want to see them in the context of a generic type that's actually interpreting them, we all have this situation, I think, from time to time where you have types that are kind of working up next to each other. No? Hello? Hello, Moto? I still didn't get a word back if it is me or if it's you. OK, here, should I turn my screen around and you can see it that way? I don't know, maybe I should. You may have noticed my style. I'll do that. My style of presenting, or my slides, they're all very gorilla and very big. So I think it's OK. I can probably, no? Huh? It's not me? What are we going to do up here?
I can explain what's on the screen.
OK.
OK, so we're in display configuration, system settings.
Oh. It's back? Hey! OK, all right, all right. All right.
You're welcome. It was the IT, I used to work in IT, so I just intimidated the machine. I said,
OK. All right. Here, we're going to do it. I got to bring this back. This is how the sausage is made, people. Nothing wrong with that. OK. OK, we'll get through it. So here's a little type. I'll just go fast. Here's a little type utility. It computes a complex type, right? And then there's a little hover. If you hover your mouse over this helper, you're going to see that, what the specific values are for this type. I realize, OK, let me back up a little bit. See the array of values up there, just an array of numbers. That's what you would have seen. So when I hover over my mouse, I'm going to get some information back. And we all use this a lot. But with 2/, that info will stay there when you're not hovering your mouse. And that's really important, because if you make another utility that finds matches for values in that array, it's like find, right? Just for an example, then you can watch the result of all of these on the screen at the same time. So they're all live. And now that means that when I'm passing the match value 1, I'll see that it matches the indices 3 and 8. But if I change my match value to either 1 or 2, it immediately updates and tells me now that the index meets that criteria. So just try it out. It's easy to find editor plugins for 2/, including if you're near retirement age. There's a Vim plugin, I think. So Orta also made an hour-long YouTube video explaining this and many more features of 2/. It's actually really cool. So then there's David Blass. You probably know David from ArcType, which is a popular validation tool with incredible TypeScript capabilities. This tool is called Attest, and it's a library for type assertions and type benchmarking with an API that's compatible with Jest, Mocha, and what's the third one? VTest. Yeah, of course, VTest. I'm about to show you a VTest example. So this assertion part is for checking and snapshotting complex types. So here we're using VTest normally, and then we're mixing in type assertions with the regular VTest stuff. And this is a topic for another talk, but if you ship types to your user, you should write tests for your types, just like you do for any other code. A lot of libraries are doing this these days, and it's going to keep going. The other half of a test is type benchmarking. It allows you to capture type-level complexity of a certain block of code. So we were talking about instantiations of types before. You can actually measure that with a test. Twitter Drama Guy made a video of this one, if you want to check it out. I ran that joke by him last night to make sure he wouldn't hate me. And he's like, however hard you're going to troll me, 10x it. All right, so we got to wrap up. Why should you care about any of this now that Go is 10 times faster? Have you heard of this phenomenon where cities just add another lane, just one more lane to the highway, but it becomes slow again later anyway? I hang around with people who do complex things with TypeScript types, and I promise you they're very excited to take those 10x gains back down to 1x by doing more complex things than that were feasible today before TSGo. So I think the reality is we're always going to need to care about this stuff. Last of all, why should you care now that AI is here? Well, if you overlay what most code looks like we were saying before, and then you put what AI is best at on top of that, you can see that AI is pretty bad at type-level programming. And I know for a lot of us, it feels like AI sucked a lot of the fun out of our jobs recently. But I think you should pep up, because what's going to happen next is you're going to see managers go from having 6 direct reports to more like 60. And that's because the power to create entire projects will be in your hands. And you won't need that middle management layer when you can prototype it faster than they can write a bunch of busy work tickets for your next sprint. So things will be much more efficient. And don't worry, they're not dying. The best of those middle managers are going to switch to being individual contributors with you. They like to build product too. And if you're new to the industry, I'd say seize the moment. Find areas like performance testing or where you can make a unique and quantifiable impact. AI leveled the playing field, so someone out of a boot camp that's great with AI can code circles around somebody who's a colleague of theirs that isn't. And if you've been doing this a while, you're not going to be able to call a favor into a colleague at their company to avoid what's next. You really do need to learn how to leverage these tools in every way you possibly can. And AI is just one of those tools alongside a type checker and a keyboard. So in this talk, we covered that understanding how the type checking stuff actually works can dramatically improve your editor LSP experience, can make or break your ability to stay within your uptime guarantees, drastically increase your iteration cycle time for AI loops. And knowing all this stuff is one of the few small remaining areas where humans can really do better. It's in your best interest to learn about those areas. So when you post those impressive PRs with big perf wins and they've just been sitting there all along, you'll be glad you spent the effort. I'm Dimitri Mitropoulos. Thanks for your time.